So air is going into what's called a converging duct. Area is 3 meters squared, and it's at a velocity of 200 meters per second. And the pressure given pressure, so pressure, velocity, we know the area and the temperature. And then it exits at an area same temperature and the pressure. Then we want to know, well, what is the velocity of the air coming out of the exit? So like last time I said, draw a picture. So we'll draw the inlet area and we'll label it. And then it's converging, which means that the area is going down. And we're given the dimensions here. I exaggerated, it doesn't go down that much. And the pressure and temperature we know. I'm not going to recopy the numbers. And over here we know the temperature and the pressure. We want to find the velocity. Oh, and we know V2 over here, right? So we look at that and we say, okay, we have areas and we want to know velocity. So we look for an equation that relates areas and velocities. So we'll say conservation of mass. Looks like a good candidate. And that is rho 1, P1A1 is rho 2, V2A2. So the same amount of mass that goes in has to come out. So the steady state flow. And so those are the assumptions. It's steady state one-dimensional flow. We're using this equation. Those assumptions go with that equation. And so let's look at the equation. What do we know? We know A1, A2, we know V2. And we know V1 and we want to find V2. But we don't know the density. So then we need to say, what other equations do we have? Here I know P1, P2, P1, P1, and P2, V2. So I can assume ideal gas. Why? Well, we're going to say air is an ideal gas. So there's another assumption. And then we can say, I need some room, so we go over here. We'll have to remember these numbers. We can say the rho 1 is P1 over P1A1. Forgot my A, R. And rho V2 is T2 over T2 times R. And we know that, we know that, we know that, we know that. So you guys do the calculation. Plug in the temperatures and pressures that I gave you and calculate these densities for me. And then we can go into this equation and get the velocity. So I'll give you a few minutes. Get your calculator out. Did you guys all get the numbers written down? Yes? So go ahead and do this. Pull out your calculator or your cell phone or whatever. Punch through these calculations. Does somebody have a number for me? What's density? Row one. Is there an exponent on it, or is that it? And the units are, okay, somebody have this one? Somebody different? You guys are all doing this, I hope. Row two? Yeah. P2, 6.08 times 10 to the fourth. Does everybody agree on these numbers? Are they good? All right, so then stick those in. This one goes here. This one goes here, and we solve for V2. So we find out that so the area speed, the velocity speeds up quite a bit. It goes from 240, right? Or 200 up to 313. Now we talked about incompressible flow, right? So we could have made our job a lot easier if we had said row one equals row two, incompressible flow. We could have knocked that out and found, in fact, let's do that. Do this in red. So what if we assume incompressible flow? So V1 is 240, A1 is 3, V2 is what we're trying to find out, and A2 is 2.5. So the units cancel out, we get meters per second. We find out V2 is 240 meters per second. Sorry, this is 200. Got ahead of myself. How good would our answer be? 240 compressible flow gives 313. That's a bit of a difference. So does this problem satisfy that rule of thumb I gave you as far as low speed flow? Remember what the rule was? It was 100 meters per second or less, or 220 feet miles per hour, right? So here we are already at 200. So this violates that rule of thumb because the velocities are too high. So it makes sense that we could not assume incompressible flow. The other deal is, right, incompressible flow says the density didn't change. How much did the density change? Changed quite a bit. What if we calculate a percent change? And I based it on row one. So if we calculate a percent change on that, so percent change at the original, that's a change of about 0.24. We get about 24%, which makes sense. That's why we got the wrong answer, is the density changed quite a bit. Now, we could probably tolerate a 5% change in density, but this is what throws the answer off. It's because as the air goes through the duct, not only does the area squeeze down and cause more air to go through, but the air expands and the density goes down. So more velocity goes through. All right, so we did the water hose problem where we did incompressible flow. This is how you do a compressible flow problem. All right, so this problem dealt with velocities, but we needed to know areas in order to solve the problem. And we also were given a lot of information about temperature and pressure. And the water hose problem, remember, we could find the velocity ratio, but we couldn't solve directly for velocity because we didn't have enough information. And so it would be nice to have another equation in addition to the conservation of mass. And we talked about how that was the conservation of momentum, or Newton's law for fluids. So that's next. All right, so this is still chapter 4. It's the next section. By the way, there's a new homework set posted that you need. Yeah, the day is on if I need to update it. It's due in class. You need to have it worked by Friday, September 11th, and then we'll upload to Blackboard the following Monday. That's next Friday is when we'll go over it in class, and then on Monday you'll upload, and then we'll do a quiz. Okay, so this is the momentum equation. Still 1D flow. And it's based on Newton's law. So really it's F equals ma, so force mass times acceleration. And what we have to do is we have to apply this to an identifiable piece of mass. Because Newton's law has to be applied to a mass, a piece of mass. We can't have stuff changing around. And so what we're going to do is we're going to look at a fluid element. This is our little box of fluid. And we're going to follow it as it moves along a streamline. So there's our box of fluid. It's going to have a velocity. And we want to track the velocity and how the velocity changes as it moves along this streamline. Remember, a streamline is following a little box of fluid as it goes. So we're going to attach a coordinate system on this called the streamline direction, a normal direction, and then Z is out of the board. So S is in the direction, the velocity there, normal is perpendicular, and we're going to track that little box as it follows S. So along the way, with this equation, we're going to neglect friction. Remember when we talked through the different types of flow, we said there's friction flow and non-friction flow. So we're going to say this is not near a surface. So there's no hard wall here with bumps that it's going to run into. There's no friction. The friction is negligible. We're going to neglect that. And we're going to say that the pressure forces on this thing are a lot bigger than gravity. And gravity is usually downward. And so it's perpendicular rather than parallel to the flow. But gravity on this thing is small compared to the pressure forces. All right. So just like before, we have to look, just like we did with the atmosphere, we look at this little box of fluid, and we want to apply Newton's law to it. So I'm going to take that box and throw it up, expand it, zoom in on it. So here's our fluid element. All right, so there's our box. And remember the axis system. This is S, this is N, and this is Z. So our dimensions are going to be, we're going to say this is some small ds in this direction. This is some small dz. And this is some small dn. And then we're going to say the pressure on this backspace, there's the S direction. So we're looking at acceleration in that direction. We're going to say that the pressure here is P. And over that little distance over to the other side of the box, the pressure might change by a small amount. Oh, and it's acting inward, right? The pressure always acts inward perpendicular. So there's our net force. So the net force, the sum of the forces equals mass times acceleration. So that's Newton's law. this thing as a density rho. Notice we're doing all of this in terms of fluid variables. Density, pressure, pressure. Don't need temperature right now. And so we're doing sum of the forces equals mass times acceleration. So that's what we're going to do down here. We have P acting forward. We have to multiply it by dN and dV. That's the area of this back space. And then we have this pressure acting backward. So that's dN dV. So there's our net force. So sum of the forces is equal to the density times the volume. And then the acceleration is change in velocity with respect to time. So really what we're going to find out here is that if the pressure increases, so if we have extra pressure over here compared to here, the fluid's going to slow down because there's a backward force on it. And if the pressure is decreasing, then it's going to speed up. Just Newton's law. A net force accelerates or deaccelerates the particle. Okay, the dN and the dV go away. And the p's cancel out. So the end result gives us, again, a differential equation because we're talking about small changes. In fact, put the ds over here, and it tells us how the pressure changes with location on the streamline related to the acceleration. So there's a little bit more we need to do with this because notice the two independent variables, at least it seems that way. We have S, which is position, and then we have time. But we know if something's moving, position and time are related, right? If you start in Wichita and you drive toward Kansas City at 100 miles an hour, what's your change in position after 1 hour? 100 miles an hour. After 1 hour, how far have you gotten? 100 miles. Well, maybe not, because you probably got pulled over by a state trooper, right, along the way, and got a ticket. You're going too fast, it's a felony, and it's called drag racing. So I guess I should have had us go on slower. 75 miles an hour. We're doing the speed limit, right? It's only if they catch you, right? I have a friend who's a state trooper, and he says there's no such thing as a speed trap. What's it called? It's called a law enforcement zone. That's what, yeah, that's what they do. So you're right. Only if they catch you. And I understand they're pretty lenient on the turnpike because you're paying customers as opposed to motorists. Although if you go too fast, you will get pulled over. All right, so that means that actually position and time are related. And in fact, velocity is change in position with change in time. And so really what we'll do is we'll use the chain rule. We'll say the velocity is a function of position, but position is a function of time. And that's how we get the relationship. So we take that equation and then we chain rule the derivative. So velocity is a function of position. That's how we want to track it. And position, we just said, is a function of time. And so we can take the dv by dt and write it as dv by ds times df by dt, right? That's just the chain rule. And that's where we see, well, here's the velocity. That's the relationship between position and time. So now we have a nice, neat differential, but it's still a nice, neat equation of pressure as a function of position and velocity as a function of position. And that's a little different than the way in dynamics we usually think of moving things. We usually think of something moving, and we talk about, well, at one time it's going this fast, and 10 seconds later it's going a different speed, right? Whereas we don't necessarily time the air going past the aircraft. What we're more interested in is what's the velocity out in front of the aircraft and what's the velocity on top of the wing. So we want our fluid variables in terms of position rather than time. So that's probably one of the biggest jumps that you have to make when you start talking about fluids and aerodynamics versus objects moving, is that you're usually talking time, whereas in the fluid flow, we're talking about that duct, right? We say, well, what's the velocity at this spot? What's the velocity at this spot? And we don't care really how long it takes the fluid to go from here to there. We want to know, well, how fast is it going in here so we can put a little airplane and test the airplane at that position. So this equation is called Euler's equation for fluid. And it's really conservation momentum, or Newton's law. And it says little changes in position lead to little changes in pressure, and little changes in position lead to little changes in velocity. And if we want to go all the way from here in the duct to here, we have to add up all those little changes as we go along. And the math way to add up little changes is integration. So that's what we do with that equation. How are we doing on time? So look at this. We're going to be integrating this differential equation. And in fact, notice there's a ds on both sides, so we can write this as just adding up little changes in dp or little changes in rho dv. And so wouldn't it be nice if this were constant in the flow? Because then we don't have to worry about how density changes as we add up the changes. All we do is add up the little velocity changes. So when we say rho is constant, what are we assuming? What do we do with conservation of mass? Rho is constant. We call that incompressible flow. Or low speed. So it'll turn out that this equation is easy to integrate with that assumption. So that's another reason we like, if we can, say low speed flow, and we're doing that. So that's what we'll do next time, is we'll derive Bernoulli's equation, which is for incompressible flow that relates pressure and velocity. If we cannot knock rho out of this equation, then we need still another equation because we have another unknown, and that will be the conservation of energy, which makes things a lot more complicated because then you got to study thermodynamics because that's the change or moving energy. So then we have to add another equation in that's thermodynamics, and we'll do that, but we're going to do incompressible flow first. All right, schedule moving forward. There's the new homework. Number 3, Friday in class, Monday, upload, and quiz. Before that, we have the holiday. So everybody take a break this weekend. Enjoy your weekend, and we'll be back here on Wednesday. The other thing that I need to show you, and I'll need to do that next Wednesday, is that the assignment requires you to fly an airplane in X-plane. Actually, you need to do a takeoff of a 777 in our X-plane. X-plane is a flight simulator. So over the weekend, if you want to, you can go to x-plane.com and download the demo, which is free, and you have to go to Legacy Downloads and get either 9 or 10. If you download 11, it requires a pretty massive graphics card. If you have a super powerful gaming computer, go ahead and download 11. But what I'll be using here is 9 or 10. You can get these for free. Go to xplane.com. Look around. They'll be. Let me go ahead and show you where that is on here. We've got at xplane.com. Now let's switch a little bit for it. It's pretty cool software. I thought this was in down here. Try the free demo. Yeah, okay, so click on that free demo button and then don't choose 11 in here. Go down to older versions. And then you can install or update Xplane 10 for Windows or for Mac. 10 is fine. Some of the stuff I'll be doing here will be in 9, but it's all the same as 9 and 10. So if you want to play around with that over the weekend, download it to your home computer and mess around with it. All right, we're done. Have a good weekend. Any questions, comments? All right.